Good afternoon and welcome to today's South African Institute of Physics webinar. I am Rudolf Erasmus from the University of the Witwatersrand and also the SAIP Council member that will be hosting this session. This webinar is being recorded and the recording will be made available on the SAIP Facebook page shortly after the conclusion of the webinar. The purpose of these webinars is to communicate with the wider South African physics community on a range of topics. The question and answer session will take place after the presenter has finished his presentation, and we ask people to then either raise their hand or type a question into the chat box or the Q&A box that they have available on the Zoom platform. So today's webinar is being presented by Dr. Martin Snow. Dr. Snow is the newly appointed SANSA Saatchi Chair in space weather. He has a PhD in astrophysical, planetary, and atmospheric science from the University of Colorado in the USA, and his expertise lies in the area of solar physics with a specialized skill set in solar irradiance measurements. During his career, he has been the lead instrument scientist on a number of satellite missions gathering solar measurements, and has valuable experience to South Africa that lies in his knowledge of solar physics and related space instruments and data. Dr. Snow is currently actively involved with research related to ultraviolet solar spectral irradiance observation and data production. He is also an instrumentalist working with calibration on satellite observatories. He has obtained leadership experience across a range of institutions and has published extensively and given many keynote and plenary addresses. He has mentored numerous students in the USA and is looking forward to working with students, researchers, and universities in South Africa to grow the expertise and capability here. He comes to SANSA from the Laboratory for Atmospheric and Space Physics at the University of Colorado, Boulder in the USA. So it gives me great pleasure to ask Dr. Snow to present his webinar with the title, New Eyes on the Sun. Over to you.
All right, thank you very much for inviting me to give this talk, and hopefully the screen sharing is working. So you already heard pretty much all of this in the kind introduction. So yes, I'm the new research chair in space weather here at SANSA, and I come from the University of Colorado Boulder, and I'm going to talk about the sun. And in particular, the new series of measurements that are becoming available now, so that you can see what's coming down the pipe. So we'll talk about the overview of the sun's interactions with the Earth. That's photons and particles and magnetic fields. And then I'll talk in some detail about those 5 missions, Parker Solar Probe, Solar Orbiter, and so on. And we'll get to each one in particular. So I'm going to start off, since it's a physics talk, right? We can show a plot and an equation, right? Just not more than one. So the plot on the left is a plot of the solar atmosphere. So the x-axis is the height above what we think of as the surface, the photosphere. Although the surface of the sun isn't like a hard surface, right? The density at the surface of the sun is about the density of the air in the room that you're in. But anyway, so height increases to the left. The solid line, well, I can use my cursor here. The solid line shows the temperature. Deep in the sun, it's in thermodynamic equilibrium almost, a little bit not, because photons need to escape. So the temperature is decreasing as you move outwards from the center. And then the temperature starts to rise. So this part of the atmosphere was called the chromosphere because original observations during eclipses showed sort of a red ring around the sun. So that was the color sphere. That's from the hydrogen Balmer alpha. And then the temperature rises sort of gradually. And then it makes a big jump in temperature up to the very outer part of the solar atmosphere, the corona. And you know, in between the transition from the chromosphere to the corona, astronomers are very clever. So the region of transition is known as the transition region. And so that's a very narrow band in the atmosphere, but the temperature rises very high. So you know, the corona gets very hot. It's millions of degrees, and we're still kind of wondering why that is. And hopefully we will learn that with some of these new measurements. And then marked on here also are sort of the formation heights of different spectral features. So that's kind of from the equation next door. It's, you know, a simplified version of the rate of transfer equation that basically says that, you know, the intensity that you see comes from about 1 optical depth into the atmosphere, which as a function of wavelength can be, you know, very drastically different for nearby wavelengths. This is kind of just the back of the envelope version of the whole equation. And so let's take a look at you know, what does that look like? So here's an image and a wavelength where you see all the way down to the photosphere. Not a lot of contrast except for some features. If you look at a slightly shorter wavelength in the ultraviolet, you start to see some of the granulation and the active regions around those sunspots. These are all from the same time. This is a line of helium-2. So it's higher in the atmosphere, almost in the transition region. You start to see very sharp contrast between the active and the quiet regions. As you get to even shorter wavelengths in the extreme ultraviolet, the sun is very optically thin at these wavelengths, so you really only see the photons generated in the outer part out in the corona. And as you get to very short wavelengths, you really only see the outer part. And so remember the spots on that little arc there. We can zoom in a little bit more. So this is a small piece of spectrum around ionized magnesium. The astronomers in the crowd will know that neutral atoms are you know, ionization state 1, and singly ionized is 2. So this is magnesium 2, near 280 nanometers. And a friend of mine has put together this movie showing the optical depth difference. That at line center, you're only seeing a much higher region in the chromosphere, whereas, you know, when you're off the line looking at the continuum, you can see much deeper in. So you can see many different features depending on how far into the solar atmosphere you can see. So the sun's interaction with the Earth is not limited to just photons. We also are bombarded by particles emitted by the sun, the solar wind, many of which then interact with the Earth's magnetic field, the magnetosphere, which in general protects us from this harsh radiation. But that the times when perhaps it doesn't is the basis of space weather, right? Why is that interesting when the sun's interaction with the Earth and our technology? So here's a set of observations from many different instruments. So this is an angular scale on both sides. So you've got on the right-hand side, the surface of the sun there in blue from stereo, I think. And I guess these are many of the different instruments on stereo. So you see the outer part of the corona. Then there's a coronagraph where you can see, you know, to a few degrees away from the sun. And then other cameras with very high gain can see features moving through the heliosphere. Those are the heliospheric imagers. So in this composite of images, you can watch you know, an eruption on the sun, send plasma all the way to the Earth. And, you know, right before it hits the Earth, we can detect it at the L1 point. but the L1 point is 1% of the way between the Earth and the sun. So by the time we're detecting it at L1, it's very nearly right on top of us. So you can see that we don't really get much warning of whether or not a feature is going to hit the Earth until it's right on top of us. Okay, so that's kind of the big picture of what we're looking at here. So what do we want to do? We want to understand the physics of the solar atmosphere, what causes the variations in the magnetic field, how those variations propagate into space, and then how the sun interacts with the Earth on both long timescales of understanding climate, but also on very short timescales, which we sort of think of as space weather. Okay, so how do we do that, right? We have a bunch of old measurements, and now we need more new measurements to help us understand even more. So I'm going to talk about these 5 missions, and I'm going to start with the one that's closest to the sun, and then move outwards all the way to the Earth. So we'll start with the Parker Solar Probe. So it was launched a few years ago in 2018, and it has the distinction of being the artificial object that has gone closest to the sun. It was only 10 million kilometers from the sun back in April. This is currently essentially orbit number 8, and it will slowly get closer and closer to the sun. On the right, you can see the view of the solar system from above with the orbit marked, and then essentially the lower panel is the distance from Parker to the sun. So it's the perihelion has been slowly decreasing. It's going to stay pretty stable from here on out through as long as the mission lasts. On the left, you can see an image of the spacecraft with a backdrop of the sun, and the big thing there is, of course, the sun shield. Right, coming that close to the sun, there's a lot of heat generated by all those photons hitting it. So all of the instruments actually are hiding behind this big sun shield. And that's one of the reasons why there isn't a camera just pointed straight at the sun, because it would just be looking into the back of the sun shield. So what does it measure instead, right? The instruments all essentially look perpendicular to the sun spacecraft line. So it's looking at the solar wind, and we want to understand how that's generated. One of the first sort of breakthroughs that it saw were these what are called switchbacks. So by the time the magnetic field gets out to the Earth, there's been a lot of turbulence, and it's fairly smooth. But in close to the sun, there are these kinks in the magnetic field regularly, and the spacecraft can fly through there and see the reversals of the magnetic field. So this is something that we had no previous measurements of. So this is brand new stuff to try and understand, how the magnetic field is generated and propagates out. Just a few more things about PSP. So it also can detect solar energetic particle eruptions from the sun. And it turns out there are many more than were expected. So they're smaller, right? So they're, on any physical distribution, right? You get a bunch of small events and fewer and fewer big events. So we had not really been able to see so many small events before. And that will help us to understand what really causes them. Ultimately, we want to be able to predict when there's going to be a geoeffective solar energetic particle event that's going to disrupt our communications and so on. The other thing that it has seen are a lot of what are called coronal mass ejections. So we often sort of refer to these as stealth CMEs because they're not nearly as bright as the sun. So a CME coming directly towards us is actually then has the bright sun as a backdrop, and it's difficult to see. So being in close and looking to the side, PSP has been able to see many more of these stealth CMEs. All right, so the next instrument I'm going to talk about is Solar Obiter. which was launched in 2020. Unlike PSP, this one has a camera, so we get to look at some pretty pictures. Although, as you'll see later, pictures aren't everything. Here's a plot of the orbit of the orbiter, right? That's fun to say. So it has gotten fairly close to the sun, but that's not its primary goal, really, is to get super close to the sun. It comes to within, say a third of an AU. 1 astronomical unit is the distance from the Earth to the sun. And so that the top plot shows sort of the distance to the sun. And then what's perhaps more interesting is the second one is the latitude. So almost every observation that we make is from the ecliptic plane, right? So somewhere along, in the sun-Earth line and the plane that all the planets are in. And so we haven't really gotten many high latitude observations of the sun. The Ulysses spacecraft did, but it didn't have a camera either. So what has Solar Orbiter seen? So one of the really interesting things are what were called campfires. Essentially, they are small flares. So they are below what we had been able to resolve before. So we didn't know there were quite so many of these tiny little flares. There are actually enough of these little flares that they could be a significant source of energy input into the upper atmosphere. So, I mentioned we don't really know why the corona is 1 million degrees. And so if there are enough of these little flares, that could provide enough heating to heat the corona. I bring back this plot of the temperature. It's sort of perhaps an average that, does the temperature vary smoothly? There are lots of hotter areas above active regions and so on. So the question is, do you get enough of these, stochastic little impulses and shock waves through the atmosphere? And so the underlying temperature structure may be much different. So that's what we hope to learn from Solar Orbiter. And then the other thing I mentioned was that it's going to get to higher and higher latitude. It takes a few years, right? That's for you orbital dynamicists, that getting out of the ecliptic plane is actually takes a lot of energy. So the reason that I think seeing the poles of the sun is going to be really interesting is that we have recently seen the poles of some other gaseous bodies in the solar system. The one on the left there, the two on the left are Jupiter. So the Juno spacecraft was able to see the poles of Jupiter, and we saw these swirls that we had no idea were there. And also, interestingly, that on the right is the polar region of Saturn, which is this big hexagon. I don't think that, sitting down with, F equals ma and figuring out the forces on the gas, you wouldn't immediately think that it's going to form a hexagonal pattern. So that's what we've seen on some gas planets recently. And in a few years, we'll be able to see the top and bottom of the sun. And, maybe we'll see something even stranger. Okay, so those were very quick. I'll be a little bit longer on the next two because I've had some actual involvement in those. So the first satellite mission I'm going to talk about is the Geostationary Operational Environmental Satellites, or GOES. So this is the GOES-R series. GOES-R, which became GOES-16, was launched in 2016. GOES-17 has also been launched. For those who don't know, so when the GOES program is making satellites, they give them a letter to identify them in sequence. And then once they are operational in orbit, then you get a number. That way you don't have any gaps in the numbering system. So GOES, R, S, T, and U will hopefully be 16, 17, 18, and 19. So GOES T will launch later this year, hopefully, I think in December. And then a few years later, GOES U will launch, and it will have the addition of another coronagraph. Right now, we have a coronagraph at L1, and if satellites, can experience upsets due to space weather and so on. So having an additional coronagraph will be essential for maintaining that observation of the sun. So each of these should last 15 years. So this is the data for space weather and a lot of solar physics for years to come. So we'll start with the Solar UltraViolet Imager, or SUVI. So it's got observes in 6 wavelength bands. And in this table shows what you learn from each one, because as we talked about earlier, different wavelengths see into different depths. And in particular, astronomers and solar physicists here like to use wavelength and temperature interchangeably, right? So normally you think like, oh, what does that mean? So here's a plot of one species, oxygen, as a function of temperature. So at low temperatures, all the oxygen would be neutral, so the fraction would all be in oxygen 1. As you heat it up, start to ionize the gas, becomes a plasma, and you start to get more population of the higher ionization states. So you can see that for a line from any particular ionization state only exists over a limited range of temperatures. So for instance, oxygen 7, is representative of, million-degree plasma. And if it gets hotter, right, it ionizes further, and you don't see those oxygen 7 lines anymore. So here's and you knew there probably was going to be a cat picture. So here's cat and cow. So this is how wavelength gets to be temperature. So when you look at the different wavelengths, you're seeing different temperature plasma or different layers in the atmosphere. So you can see the 6 different wavelengths separately, and then you can also use some knowledge of what those temperatures represent to then create what we call a thematic map. So this says that when you add together these 6 images in the right way, that combination of temperatures would be, say, a prominence or a bright region, and so on. I like to highlight this one because in my former life, before I became the research chair, one of the programs I had was a research experience for undergraduates in the United States. And one of the summer students, who was a brilliant researcher and is now a graduate student at CU, essentially designed this system using machine learning over a summer. So it's amazing what undergrads can sometimes accomplish. All right, so let me check on the time here. I'm doing okay. So the other thing that SUVI is adding to our knowledge base, as opposed to what we currently observe. So if you've seen pretty pictures of the sun in the ultraviolet, they probably came from the Solar Dynamics Observatory, the AIA, the Atmospheric Imaging Assembly. And so what I'm showing here is the difference in field of view between all of those instruments. So the little square, was the TRACE satellite from several decades ago. And then the AIA field of view goes out to 1.3 solar radii. So you see all of the disk of the sun and a little bit of the corona. All right, so the blue box is the SUVI field of view. So I'll give you an example of what you would like to see. So here's a movie from SUVI, and I cropped the movie to what AIA would see approximately. I see I didn't quite get it centered, but you'll see it all in a minute. So you can see that on the right-hand side there's an eruption. You see it have an influence over much of the disk of the sun, and now you can see the post-coronal loops forming and so on. And you wish you knew just what was happening beyond the edge of this field of view. So now you look at that same movie from the full SUVI field of view, and you can learn a lot more about how the magnetic field evolved during that eruption. And you can see the whole loop structure. you can see there before the eruption and then afterwards. Another thing that SUVI provides that AIA didn't is, you can do multiple integrations at different gain levels, different exposure times, and so on. And you can then make an HDR image, a high dynamic range, just like your phone does, where you combine short exposure with a long exposure, so you can have information about bright regions as well as the darker background. So the image on the left cropped out the part that AIA can't see because it's out of the field of view. And then also you can see the overexposure and the blooming as the CCD is read out. And so with the HDR mode on SUVI, we can understand flares much better. All right, and so you can get all of this data today from NOAA. There's the web page. You can get, you can connect your API and download it automatically and so on, or you can go look at particular times of interest. So that data is all available there. The other instrument on EXIS is one that I worked on personally. So for the 4 instruments in the GOES-R series, they essentially were all made at the same time to save money. There they are in the nursery. And then there's a close-up image of just one of them. And on the front plate there, you can see the buffalo, which was the logo of the university. Unlike, official contractors, universities have a little more latitude on, putting their stamp on there. We hadn't actually told NOAA that we were gonna do that to the front plate until the instrument was delivered. And then they looked at it and they're like, oh, that's kind of cool. So then they put out press releases and took credit for it. So anyway, so what does EXIS do? So it measures extreme ultraviolet and X-rays. And so here's a brief mention of why that's important. The events on the sun have an impact on the upper atmosphere of the Earth. On the left, you can see we use high frequency radio communication to talk to airplanes, so that we know when they're lost or anything. We communicate with GPS satellites all the time for high precision surveying and everything else. The activity on the sun also puffs up the outer atmosphere, increasing the drag on satellites. So in order to correctly model satellite drag, we need to know the solar input as precisely and as often as we can. So that's kind of what the goal is, and here's how we do that. So on EXIS, there are essentially 4 measurements. The X-ray sensors in what are known as long and short wavelengths, right? So long wavelength means, all the way out to 8 angstroms. And the short is, from essentially 0 to 4 angstroms. And then, so those measurements have been made for, since the space era back in, the late 70s. This new version of this instrument also has 3 spectral channels. So one of them is the shortest wavelengths, measuring a line, iron 15, from the corona. The main line in the B channel is hydrogen Lyman alpha. And then the C channel, which is the one that I worked on in particular, measures a piece of spectrum around the magnesium 2 lines that I showed you in that earlier movie that are representative of the chromosphere. So in each of the other channels, the B and the A, there are some lines from the region of the sun that the other one is measuring. So you get the chromospheric lines in red. So in the B channel, we have a couple of chromospheric lines as well as the transition region lines. And then in the A channel, there's the coronal lines, but then there's also contribution from the transition region. So if you could measure one of them carefully and accurately over time, right, you could use that to correct degradation in the other channels. And that's what we call the bootstrapping. All right, so why would we pick 280 nanometers? So here's a little piece of the ultraviolet spectrum from the SOLSTICE instrument. So the top one is the spectrum, and the second one is the ratio of two spectra taken 2 weeks apart. So the sun rotates about once every 27 days. So if you look at spectra 2 weeks apart, you essentially see two different sides of the sun. And you can see that the variability drops from like 5% down to almost nothing. But then near 280, there's a big spike in the variability, right? And that is that if you measure the variation of the core of this magnesium-2 doublet, you're looking high in the chromosphere, whereas the nearby wavelengths are looking all the way down into the photosphere, which is much less variable. So by taking the ratio of those two nearby pieces of spectrum, you can create a very stable proxy for solar activity that isn't dependent on absolute calibration, right? So other instruments measure this. It depends a little bit on spectral resolution, but once you correct for that, right, you have this relative measurement that is good all the way back to 1978. All right, so what does it measure, right? So the X-rays vary by a factor of 1,000 when there's a flare, right? You're hopping along at 10 to the -6 watts per square meter, and it boom, a flare appears. Sun is suddenly 1,000 times brighter for minutes or hours, right? This particular flare lasts for several hours and then may slowly decrease. When I said there were just the two solar instruments, it was not quite true because there's also particle sensors. So you can see that the particles took a little bit longer to get to the Earth than the sun, than the photons, right? Photons travel at the speed of light, and the particles can be relativistic. They can travel at half the speed of light or a quarter or something like that. So there's a slight delay before they arrive, but eventually they do arrive and cause noise. That's all that they're good for, right? Don't let any of those particle physicists hear that. Okay, so here's the other spectral channels that I showed you before. One thing that you'll kind of notice, this is the same time interval as that one. So, here there's a lot of little bumps. I guess they're flares, but they're only a factor of 2 or something, not this factor of 1,000, right? This is a log scale. But at other wavelengths, maybe you don't see those at all because they're formed higher up in the atmosphere, so they're not disturbing the chromosphere or lower levels. One thing that you may notice here is that all of the instruments show a gap here. That's when the spacecraft went behind the Earth. It's difficult to see the sun from behind the Earth. And at some wavelengths, like Lyman alpha, right, the Earth has an extended exosphere of hydrogen. And so you start to get absorption before you get into eclipse. And I'm part of another project where we're actually then trying to map out the hydrogen density, several Earth radii away as using this data. So it's not just blocking our knowledge of flares. All right, and then we get on to the C channel. So this is the ratio of the emission cores to the wings of the line. So it's called the magnesium-2 index. So EXIS measures it every 3 seconds, and which is more than has ever been measured before this. It used to be measured once a day. So you can see that the fractional change is much smaller, right? This is not a factor of 1,000, it's like 10% more. But when you look at the energy in the solar spectrum as a function of wavelength, right, you get up here to these longer wavelengths. And so a small change here ultimately is a lot more energy change than these shorter wavelengths. So this is a measure of high importance for understanding the changes in the ionosphere and above. So this is what's new from EXIS. You can see flares at these other wavelengths now that we didn't see before. So we plotted here. They've all just been normalized to the peak of the X-rays here. So the black curve shows the X-rays. So there's a big peak and then a secondary peak. What's interesting is that the transition region lines and the chromospheric lines actually peak earlier than the X-rays. So before this EXIS instrument, right, we just had the measurement of the X-rays. And one of the goals of space weather forecasters is they're watching the X-rays and they see it rise, and by figuring out how quickly it's rising and so on, you get some estimate of how big the flare might be and when it will peak, so you can warn the power grid and the satellite operators and so on. Right. What's interesting is that these new wavelengths at such high time cadence actually, for some flares, peak earlier than the X-rays. So they will give extra warning to the space weather forecasters here at SANSA and those other places like NOAA and so on. Another really interesting, okay, so there's the understanding the timing of flares is what we're working on. Another thing is you may have heard of solar oscillations, and the study of acoustic waves inside the sun is called helioseismology, similar to seismology here on Earth. And the surface of the sun is pulsating at many frequencies. And this magnesium-2 measurement is now at a high enough time cadence and a high enough signal to noise to start seeing these oscillations that previously were only seen at visible wavelengths from the ground. So this is yet another tool for helioseismology. And this data, even though it was launched in 2016, so 4 years ago, the wheels of bureaucracy sometimes grind slowly. So this data is just recently become available. So all these new instruments on EXIS, are now available from NOAA, but you may not have heard of them much yet because they were not public until very recently. So here's the URL for data from EXIS, which you can also get from the NOAA webpage. All right, moving on to another instrument that I've been involved in on a mission called the Total and Spectral Irradiance Sensors, or TSIS. So this instrument package is on the space station, which presents some interesting challenges because docking and solar panels and everything get in the way. But it is a good place to have an instrument. So there are two instruments in TSIS. One measures the total irradiance using what's known as an electrical substitution radiometer. The way that works is you have one channel exposed to the sun. It heats up from the sunlight. And then you have another channel which is shuttered. And then you heat it using, essentially resistance in wires, right? So, and then when the two are in balance, you know how much energy you had to put in electricity in order to balance the energy in the sunlight. So that's how, vaguely how an ESR works. And so the total irradiance monitor essentially measures the integrated spectrum, what used to be called the solar constant. It does vary, as I'll show in the next plot. And it has 4 redundant channels to try and get as high an accuracy as possible. There is also a spectral irradiance monitor. So it's a prism spectrometer as opposed to a grating, mostly because you want to measure over such a wide wavelength interval that's difficult to do with a single dispersing element. But with a prism, you can do it. And then it also has a little ESR. And there are 3 channels which are duty cycled to measure the degradation. So here's the time series. The lower plot is the time series of the TSI. So the solar constant varies by about 0.1% on an 11-year period. And you can see that we've stitched together this composite from many different instruments, right? The only way you can do that is by knowing their absolute calibration and their degradation, and potentially having some overlap in the measurements. So we've done that with the TSI. The SSI measurements for much of the spectrum, essentially all the visible light and infrared, only started with the SOURCE mission back in 2003. So we plotted there in red the time where the SOURCE mission started, and then we've continued that with TSIS-1 and with what I'll describe as the compact SIM. All right, so we want stable measurements, right? Everyone's laughing, I hope. All right, so what sort of accuracy can you get from a spectrometer? So this TSIS has been able to pioneer essentially to fractions of a percent calibration over from 200 nanometers out to 2,000 nanometers and beyond. So this is quite an achievement. And how do you do that? One way is you need a stable light source. So we have this system. I don't remember exactly what CIRCUS stands for. Something about irradiance. So you have this stable set of lasers shining into a vacuum chamber. And then you have on the left here, you have a cryogenic radiometer. That's the best way standards, people who can measure irradiance. And then you have a mirror that you can flip to the other position to send that same beam of light to the instrument. So by switching back and forth, as long as the switching is related to the time scale of stability of the lasers, right? You can average together many measurements to understand a calibration of this instrument relative to the radiometer. And so here's a sort of plot of switching back and forth between them, and the radiometer itself has an uncertainty of 0.07%, k = 1. And then, once you fold in things like how repeatable is moving that mirror and how stable are the lasers and so on, you get to the magic number of, a little over 0.1%. So that's quite a step forwards. Okay, so what do you learn, right? So when you integrated the whole spectrum, it only varied by 0.1%. And that's true of much of the visible spectrum. As you get to shorter wavelengths, of course, as we kind of have known for a while, the variability goes up, right? This is the log of the wavelength here. So this is the magnesium 2 line, this one, the spike here. So you have higher variability at the shorter wavelengths, but you can see that there's much more power at the visible light. So 0.1% variability at visible wavelengths is probably more energy than a 10% variation in the ultraviolet. It heats different parts of the Earth's atmosphere. So you want to know about all of them, but this is why you need to make this measurement very carefully. And when you go out into the infrared farther, you actually see deeper into the sun, and there the sense of variability is reversed. That it's out of phase when the sun is more active in the outer parts. It's actually darker deep in. So that's kind of an interesting thing to understand. Here's just a couple of time series of measurements at different wavelengths. So plotted the 280, the ultraviolet, sort of the visible and so on, and marked where they come from in the atmosphere. You can see that the variations are bigger in the ultraviolet, but still very important at the longer wavelengths. All right, I'll quickly talk about the 3 versions of SIM. So one launched back in 2003, went for 20 almost 20 years. The TSIS SIM launched in 2017, hopefully will last several more years. And then of course, ultimately you want to be able to put instruments into space cheaper and faster and so on. So we've scaled everything down by a factor of 10 for a 6U CubeSat version. And we'll launch a total irradiance monitor on a 2U version in the near future. I'll just talk one little technology advancement. Instead of black paint, which was what old radiometers used to use, to nickel phosphate, which is what was used on the source instruments. And now we use these vertically aligned carbon nanotubes. So they grow crystals and essentially any photon that hits there, you want to capture it. Right? You don't want it to reflect off and then have to capture it again somehow. So the blacker the better. And so these carbon nanotubes are a new technology that's used on the compact SIM. That's pretty cool. And of course, you can get that data. You can get the daily average or a 6-hour average or whatever at many different wavelengths from LASP at the University of Colorado. All right, so the last instrument that I'll talk about is still kind of in the commissioning phase. So very little has been released, but it's all very interesting. So this solar telescope has a 4-meter primary mirror. For those of you who have been in the astronomy community, a 4-meter mirror is not to be sneezed at and or sneezed on. And now to point that thing at the sun, right? You're going to capture a lot of photons. So you can throw away most of them and you still get really interesting information. You'll measure the polarization of everything, get the full Stokes parameters and so on. Here's kind of the first light image. These guys are Americans, so they'd say, well, okay, let's compare this to Texas, right? But no, more importantly, let's compare it to the size of South Africa. So the DKIST telescope can see things that are, essentially the spatial resolution is 30 kilometers. And that is more than a factor of 10 better than any previous ground-based telescopes. Here's the first light image. So this is essentially 10 minutes compressed to just a few seconds, of course. But you can see these bright regions at the cell boundaries, as contrasting with the normal downflows, the dark regions on the other cells. So this is all hot off the press from a year ago. I think COVID has slowed things down a little bit. All right, so we're getting to the summary phase here. So this is an infographic put together by the National Science Foundation in the US, comparing DKIST and Solar Orbiter and Parker Solar Probe. One thing I find interesting, of course, is the ground-based mission is 44 years and the space missions are maybe 7. Might get a little bit more time out of them, but not too much. And so you get a 4-meter telescope on the ground. There's no way you could launch a 4-meter telescope into space. The Hubble Space Telescope is like 100 centimeters. No, sorry, 1,000. And the Solar Orbiter telescope is actually only 12.5 centimeters. But since it's closer to the sun, that's sort of like a 50 centimeter telescope at the Earth. So you can see that DKIST is still going to get much higher spectral resolution. Of course, you're looking through the atmosphere, so you can't look in the ultraviolet. But the combination of being able to see the right wavelengths as well as the spatial resolution will teach us more and more about the sun. So there's that. And I like the image resolution, right? 330 football fields. I guess those are 100-meter football fields. 2,000 for that. And yeah, Parker doesn't have a camera, so no image resolution there at all. All right, so we'll just summarize here. So these new eyes on the sun are from new locations, right? Parker Solar Probe is closer to the sun than anything's ever been before. Solar Orbiter is going to be at higher latitudes than are possible from the Earth. So that's what's new in the locations. These solar measurements use new technology. So the better calibration of the instruments, so you can combine measurements from one instrument with another. And also then the technology of the carbon nanotubes as detectors in space. So that's all new. The new operational capabilities. So SUVI has this wider field of view. You can watch the eruption of flares and so on the sun better than ever before. And EXIS provides new wavelengths that have not been seen at this space weather cadence before. So those will both provide much greater sources of information for space weather forecasting. And of course, this enormous 4-meter dish at the top of a mountain in Hawaii is going to produce the best images of the sun and that we've ever had before. So that's kind of the group of them. And I thank you, and I'll welcome any questions you might have.
Thank you very much for that presentation. I much enjoyed. Okay, so we can accept questions, please. You can either put up your hand or type a question in one of the Q&A or chat boxes that are available. And I know from experience that often takes a minute or two for people to type a question when they should, when they formulate.
Right. They're busy with their hand in the air before they realize, oh wait, I need to put it at the keyboard.
Indeed. There's something from my side. I know in the sort of general media recently there was talk about differences in opinion about the intensity of the coming solar cycle. Different models leading to predictions of it either being much more intense or less intense than the current cycle. So what is the most recent thinking that you're aware of?
So the way that you try and predict the size of the next solar cycle often depends on the strength of the magnetic field at the poles, yes. Which is difficult to see. Looking at all of the traditional means of prediction for the next solar cycle indicate that it should be small, like the one that we were just leaving, cycle 24. So cycle 25 would be predicted to be about the same low size by the majority of folks. But some friends of mine in the US have used a different method combining 140 years worth of data and trying to predict when the news cycle really kicks off and so on. And they actually predict that cycle 25 will be bigger than we've seen for many decades. So there's always a few outliers in any prediction. I think this Terminator way of predicting the next solar cycle, it has some merit, but as a famous saying is, prediction is difficult, especially about the future. So I think we will know within a few years whether the next cycle really is bigger or not. But yes, the consensus is that it will be a small cycle, but there are still some mavericks who will say that no, it's going to be big.
No, thank you. So the data will prove which camp has got their modeling right.
Yep.
Okay, I don't see any specific other questions at this point. Let me just
somebody
check
has
out.
Raised their hand.
Yes, I've just seen that. So let's just Brian, there we go. Yeah. There we go. Lebogang, you can unmute yourself and then ask your question. As far as I know, yeah, I think you should be able to unmute you. Lebogang, can you unmute yourself? Okay, there seems to be a hiccup there.
Yeah. Tebogo, can you try and check if you can unmute that person?
No, I can't. I've been trying that. Just saying us to unmute.
Okay, all right.
We have allowed the person to speak, but now she needs to unmute herself.
Yes. Okay, so in other words, Lebogang, you need to click on the microphone icon in Zoom to unmute. Okay, while we wait for that, are there any other questions perhaps?
I can take questions by email in the future if you like as well.
Okay, no, thank you very much for that, that offer, much appreciated. Okay, it doesn't seem like Lebogang is having any joy with unmuting the microphone. Right. So I'm sure you can, in that case, the question can go to you via email.
Zip back to my first slide, which had my email address. I guess I should have put it on the last slide too.
Indeed. Although people can also go and look at the recording, and then they should be able to just, grab the first slide with the information, relevant information.
There we go.
Thank you very much. Perhaps the last question from my side is just I mean, one of the other hot topics where a lot of information input is needed is long-term climate change and climate modeling. Is there a significant impact on that type of modeling that's being opened up by the additional information that is being provided by these extra satellites and sensors?
Oh, definitely so. So, before climate modelers that didn't have access to the data, right? I mean, you make your model do what it can. So they usually just use the total solar irradiance, the TSI, that measure, changes by 1/10%. And, maybe you then tried to create a proxy model for just a few wavelength bands. I think, before the source mission, it was common for climate models to use, say, maybe 8 wavelength bands, and just average over the entire ultraviolet or so on. Whereas now that you have a better understanding of the variability as a function of wavelength, you can start to put in specific atomic transitions into your climate model. The OH band or whatever doesn't have to be lumped in with everything else. And you can look at just that variation. Ozone is, of course, also an extremely important measurement in the upper atmosphere. So knowing how the ultraviolet varies, which guides the destruction of ozone as well as the creation of ozone. So knowing how that varies over cycles or even seasonal variations is something that has opened up a lot of atmospheric science observation, modeling. In terms of the long-term influence of the sun on climate, I think there's still a fair amount of controversy in the world about that.
Yes.
The sun's contribution is perhaps 10% of the change at most, but that doesn't explain why the temperature has shot up over the last 50 years because the sun hasn't changed that much in the last 50 years. So, but yes, the new observations definitely have opened up a lot of new avenues of understanding the Earth's atmosphere in a climate context.
Okay, good. Thank you very much. Right, I think in the absence of any other hands or questions, it remains for me to thank you very much for a very interesting presentation. Thank you for the time you've taken to talk to us and for showing us what you bring and what you're involved with. I found it very interesting. Thank you very much.
Yep. All right, well, thank you.
And also thank you very much to the SAIP office in the background. They're responsible for organizing and running the Zoom session, and their help is always indispensable. Thank you very much to them. And thank you very much to all the attendees who made time to log in and listen to the presentation. So this would be the last webinar for the first semester of the year. We'll take a short break and then start again in the middle of August 2021. So thank you very much. I wish you a good afternoon and a good weekend. Goodbye.
All right. Thank you.